Welcome back to Computer Lessons.
We have successfully built the body with the motherboard, installed the brain with the CPU, and given it short-term memory with the RAM. But if you were to press the power button right now, you might face a disappointing reality. Depending on your CPU, your monitor might remain completely blank, or it would struggle to draw even the simplest 3D shapes. To turn this machine into a gaming beast, a video editing powerhouse, or a portal to virtual worlds, we need a specialist. We need the rockstar of the computer world. Enter the graphics card, or the GPU. This is the component that costs the most, consumes the most power, and creates the most excitement among enthusiasts. But what exactly makes it different from the CPU? Why do we need two separate processors in one computer? Let's use a specific analogy to understand this relationship. Imagine the CPU, the central processing unit, as a brilliant mathematics professor. He is incredibly smart, capable of solving complex calculus, writing poetry, and managing the entire university administration. However, there is a catch to his genius. He works sequentially, meaning he can only focus on one or two difficult tasks at a time. Now, imagine we want to render a scene from a modern video game. A standard 4K monitor has over 8 million individual pixels that change color 60 to 144 times every second. That requires hundreds of millions of calculations per second. If you asked the professor's CPU to do this, he would fail miserably because he is too slow at doing millions of tiny, simple tasks at once. Enter the GPU, the graphics processing unit. The GPU is not a single professor. It is an entire army of elementary school students. Individually, these students are not very smart and cannot run an operating system or perform complex logic. But if you give each of them a crayon and tell them to color one single pixel, they can paint the entire screen in a fraction of a millisecond. This is the fundamental difference between the two. The CPU is designed for serial processing, while the GPU is designed for parallel processing. Let's look at the physical card itself, which is often the largest component in the case. Unlike the CPU, which is a tiny chip hiding under a cooler, the graphics card looks like a brick. That is because a graphics card is essentially a computer inside a computer. It has its own motherboard, which we call the PCB, and its own dedicated brain, the GPU die. It even has its own system memory, which we call VRAM, or Video RAM. You might have 32 gigabytes of system RAM, but your graphics card has its own dedicated 8, 12, or 24 gigabytes. Why does it need its own memory? Because the GPU needs data instantly, and the distance to the system RAM is simply too far. System RAM is fast, but VRAM is essentially turbocharged. It uses a technology called GDDR, or Graphics Double Data Rate, which is designed for massive bandwidth. Think of it like a fire hose of data. It blasts textures, geometries, and lighting maps directly into the GPU core at speeds that make system RAM look like a garden hose. If the GPU had to wait for the system RAM to deliver data, your games would stutter, freeze, and become unplayable. Now let's dive inside the chip itself. Inside an NVIDIA card, you have CUDA cores, while inside an AMD card, you have stream processors. These are the tiny workers we talked about earlier. A high-end card might have 10,000 or 16,000 of these cores working in perfect harmony. For decades, the primary job of these cores was something called rasterization. This is the traditional way of making 3D games. It takes 3D shapes called polygons, flattens them onto your 2D screen, and paints textures on top of them. It is a fake way of creating a world because it simulates light by just painting shadows where programmers think shadows should be. But recently we entered a new era called ray tracing. This is considered the holy grail of computer graphics. Instead of faking the light, the GPU actually simulates the physics of light particles, or photons. It traces the path of a light beam as it bounces off a car hood, reflects onto a wet puddle, and then hits the camera lens. This involves incredibly difficult math calculations. It requires billions of intersections to be calculated per second. That is why modern GPUs have dedicated hardware, called RT cores, just to handle this specific math. Without these cores, ray tracing would bring even the fastest traditional GPU to its knees. But the GPU is no longer just for gaming. Remember those thousands of tiny students we mentioned? It turns out that parallel structure is perfect for artificial intelligence. When you talk to ChatGPT or generate an image with Midjourney, you are using a GPU. Deep learning involves training neural networks with massive amounts of data, which is essentially a giant matrix multiplication problem. GPUs happen to be the kings of matrix math. This is why graphics cards became so expensive during the crypto mining boom and why they are now the most valuable hardware in the AI revolution. Let's talk about the physical installation, which scares many first-time builders. The graphics card plugs into the top PCIe slot on your motherboard, the X16 slot we discussed in the last video. But be careful, modern cards are heavy. Some are so massive they can actually sag under their own weight and damage the slot over time, often requiring a support bracket. They are also incredibly hungry for energy. The PCIe slot itself can only provide 75 watts of power, but a monster card like an RTX 5090 can consume 500 watts or more. That is why you see those thick cables running from your power supply directly into the side of the card. If you don't plug those cables in, the car simply won't start. And all that power creates a byproduct: heat. A lot of heat. That is why the card is covered in fans and a massive radiator called a heatsink. Under load, a GPU silicon can reach 80 or 90 degrees Celsius. The fans ramp up, sometimes sounding like a jet engine, to push that heat away from the delicate silicon. If the cooling fails, the card will slow itself down to prevent permanent damage. This brings us to a crucial concept for every builder: the bottleneck. You need balance in your system. If you buy the most powerful graphics card in the world, but pair it with an old, slow CPU, you are wasting your money. The GPU will draw the frames incredibly fast, but it will have to sit and wait for the slow CPU to tell it what to draw next. This is called a CPU bottleneck. Conversely, if you have a supercomputer CPU and a weak GPU, your games will look like a slideshow. Building a computer is not about buying the most expensive parts. It is about finding that harmony between the brain and the artist. So, the graphics card is the artist. It is the brute force that paints the digital world. It has evolved from a simple display adapter to a supercomputer that powers the AI revolution. We now have the brain, the memory, the skeleton, and the artist. But we are missing something vital. All this work, all these calculations, where do we put them when we turn the computer off? We need a vault. We need long-term storage that doesn't forget. In the next video, we are going to explore the war between the old spinning hard drives and the lightning-fast SSDs. We will learn how computers remember things forever.
Make sure you're subscribed so you don't miss the next class. Let me know in the comments, what was the first graphics card you ever owned? Mine was a Voodoo 2. If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.